Okay, sample problem 17.1. Determine the pH at 25 degrees Celsius of a solution prepared by adding 0.050 moles of sodium acetate to 1.0 liters of 0.10 molar acetic acid. Assume that the addition of sodium acetate does not change the volume of the solution. Okay, so here's what we're going to do. This is a problem involving acetic acid. Acetic acid is one of our weak acids, so I'm going to write its chemical formula here. And I'm going to look up the Ka value. This is all from chapter 16, so keep in mind as you do these problems in chapter 17, you may need to go back to chapter 16. You will need to go back to chapter 16 to find certain things. The chemical formulas of the weak acids or the weak bases, the Ka values or Kb values as well. So for acetic acid, the Ka at 25 degrees C is 1.0 times 10 to the minus 5. Okay? So here's what we're going to do. We're going to set this up as a general acid-base chemical equilibrium problem. It's a weak acid, and remember, weak acids, just like strong acids, they can react with water. It's just you don't get as much of the hydronium out of a weak acid, right? Instead of getting 100% ionization, you get 1% ionization, perhaps. Or 2 or 3. Okay? So there's the reaction. Remember, we're treating acetic acid as a Bronsted-Lowry acid. It's donating the hydrogen ion, the proton, to the water. So you get hydronium and the acetate. So let's put in our initial concentrations. Okay. So our initial concentration here is 0.10 molar. This is initially 0, but the acetate now is no longer 0. Okay, that's an important aspect of this. It says that it's actually going to be 0.05 moles in a liter. So 0.05 divided by 1 is 0.05 molar. Okay, so that's how this differs from the chapter 16 problems of weak acids. This is a mixture of the weak acid with its conjugate base. Okay, so we got to figure out what the direction is going to be. This is the initial. It's either going to go to the left or the right, but keep in mind what happens. We calculate Q. Q is hydronium, 0, times acetate, 0.05, divided by acetic acid, 0.10. That's still equal to 0 because the hydronium is 0. So that means the reaction is going to go to the right, so that hydronium is not 0. So then at equilibrium, we have 0.10 minus x, we have x, and we have 0.05 plus x. So again, these are equilibrium concentrations. What differs in this problem is it's 0.05 plus x, not just x. Okay? So that means that Ka is 1.8 times 10 to the minus 5 is x times 0.05 plus x, right? Products over reactants, 0.10 minus x. Okay? Now, what do? We could run this through the quadratic formula, right? Multiply everything together, go through ax squared plus bx plus c equals 0. Solve for x, get the pH and all that kind of stuff. Okay? We're trying to find the pH, right? But, again, this is a weak acid. And 0.10 or 0.05, those are pretty big numbers compared to 1.8 times 10 to the minus 5. So let's go ahead and simplify like we have. X, 0.05 plus x would be 0.05. And 0.10 minus x would be 0.10. Turns out it's a pretty good assumption for this problem because those initial concentrations are so large to the value of Ka, it's going to be definitely all right. So now we're going to solve for x. So solve for x, let me write it down here again. 1.8 times 10 to the minus 5 is equal to, now let me write it a little bit differently. Let's write it as 0.050x divided by 0.10, right? I'm just writing the 0.05 before I'm writing the x. So if we want to figure out what x is, we're going to multiply both sides by 0.10, and then we're going to divide both sides by 0.05. So we would have 1.8 times 10 to the minus 5 times 0.10 over 0.05. And that would be equal to x. Well, 0.10 over 0.05, the authors of this problem made the numbers easy. 0.10 over 0.05 is 2. So 2 times 1.8 is 3.6. So 3.6 times 10 to the minus 5 is equal to x. Okay, so if we want to calculate the pH, it would be the negative log of that, right? So there we go. So 3.6 times 10 to the minus 5, negative log of that. So 3.6 times 10 to the minus 5, negative log, 4.44. Now I want to point out in the lecture problem for this section, if we had just had 0.10 molar acetic acid with no acetate added, the pH would have been 2.87. So notice the pH is much higher. This is the common ion effect in effect. The common ion effect says that if you add the conjugate base to the weak acid, it will have the effect of pushing the equilibrium back, the Chatelier's principle, back toward the reactant side, which will have the effect of reducing the amount of hydronium that goes down, so the pH will go up. And in this case, it went from 2.87 to 4.44. A very important result of Le Chatelier's principle. Common ion effect for a weak acid problem.